Welcome to the Explainer. Today, we are cracking open one of the most powerful and, let's be honest, complex pieces of technology out there, the Oracle database. We're not just going to list off its features. Oh no. We are going to deconstruct it piece by piece so you can build a solid mental model of why it works the way it does and how it manages to be both incredibly fast and unbelievably safe with your data. So here's our game plan. We're going to start with the most fundamental concept of all, the split personality of an Oracle server. Then we'll look at the actual files sitting on the disk. From there, we dive into the living, breathing part, the memory and the processes that do all the work. We'll even follow a single query on its journey from start to finish and see how Oracle handles changes without ever breaking a sweat. And by the end, you'll see how it all clicks together into one seriously impressive system. All right, first things first. Before we can talk about anything else, you have to get this one concept down because literally everything else builds on top of it. An Oracle server isn't just one thing. It's actually a partnership between two completely separate halves that work together. And this slide nails that separation perfectly. On one side, you've got the instance. Think of this as the brain. It's all the memory structures, all the active processes. It's the part that's actually thinking and doing the work. But here's the catch. It's totally volatile. It lives in RAM, so if you pull the plug on the server, poof, the instance is gone. On the other side, you have the database itself. This is the body. It's the physical collection of files on your hard drive, your data, your logs, all of it. This part is persistent. The brain is temporary and active. The body is permanent and, well, kind of passive. This split is the absolute key to Oracle's performance and its rock-solid recovery. Okay, so let's start with the body, the stuff you can actually see in a file explorer. These files are the permanent physical foundation of everything that happens in the database. So there are three types of files that you absolutely cannot live without. First, the data files. Pretty straightforward, right? This is where your actual data lives, all your tables, your customer info, product lists, you name it. It's all neatly organized in these little chunks called blocks. Next, and you could argue this is the most important file for safety, are the redo log files. Think of this as the black box flight recorder for your database. It records a description of every symbol change that happens, in order. If your server ever crashes, this log is how you rebuild everything perfectly. And finally, you have the control files. These are small, but they are the master blueprint of the entire database. They know the database's name, when it was created, and most importantly, the exact location of all the other data files and redo log files. If you lose the control file, Oracle has amnesia. It has no idea what it is. Now, besides that main trio, there are a few other key players. The parameter file is basically the instruction manual for the brain, the instance. When you start Oracle up, it reads this file to figure out, okay, how much memory should I use? What features should I turn on? Then there's the password file. This is like a special backdoor key for administrators. It lets them connect and manage the database even when it's not fully up and running, which is obviously crucial for startup and shutdown. And last, but definitely not least, we have archived redo log files. Remember that flight recorder? Well, the main log files get reused and overwritten. Archiving creates a historical copy of those logs. This is your ultimate insurance policy. If your whole server melts, you can take a backup from last night and use these archive logs to play everything forward, right up to the second before the disaster. Okay, we've got the physical body down. Now for the fun part. Let's bring it to life. We are now officially moving into the instance, that volatile, super active world of RAM. This is where all the magic happens. Right at the center of the instance is this huge chunk of shared memory called the System Global Area, or SGA. And the most important word there is shared. Picture a giant open plan workshop. Everyone who works on the database, every user, every process, comes to this one central place to work. This is a huge deal for performance because it means Oracle doesn't have to waste time and resources giving every single user their own private workspace. It's what makes it so incredibly scalable. So, the first section of our workshop is the shared pool. This is like the library and the strategy room combined. It holds on to the execution plans for queries. See, when you run a query, Oracle works really hard to figure out the fastest way to get your data. The shared pool remembers that plan, so if you or anyone else runs the exact same query again, it can just grab the plan and go. No need to reinvent the wheel. It also caches metadata, information about your tables and columns, which just speeds everything up. Okay, next up is the database buffer cache. Now, if the shared pool holds the blueprints and the instructions, the buffer cache holds the actual raw materials, the data blocks themselves. Let's be real, reading from a spinning hard drive is painfully slow. So what Oracle does is it copies the data you're using from the disk into this super fast memory cache. And trust me, accessing data that's already in RAM is thousands of times faster. The single biggest bottleneck in any database is disk I/O, and the whole point of this buffer cache is to avoid it as much as humanly possible. And this little guy, the redo log buffer, is the memory component that makes Oracle so bulletproof. It's a small area in the SGA. Now here's the clever part. When you change some data, Oracle doesn't immediately write that big, clunky data block back to the slow disk. No way. Instead, it creates a tiny little note that just describes the change you made, and it scribbles that note into this super fast redo log buffer. This is the heart of a concept called write-ahead logging, and it's brilliant. It guarantees that a record of your change is safe before the change itself is made permanent. So we have this massive shared workshop, the SGA, with all its different sections. But who's actually doing the work? Who's carrying things around, cleaning up, and making sure everything runs smoothly? Well, that's the job of a dedicated team of worker bees, the background processes. These are specialized programs that fire up the moment the instance starts, and they just work nonstop. And this table shows you the A team. Each one has a very specific job. You've got the database writer, or DBW. Its only job is to write changed data blocks from the buffer cache down to the physical files. It's designed to be lazy, writing in big, efficient batches. Then you have its hyperactive cousin, the log writer, or LGWR. Its job is to frantically write everything from that little redo log buffer down to the actual redo log file on disk. This is the guy that makes your transactions permanent. Then you have the cleanup crew, SMON, the system monitor, handles recovery and other system chores. And PMON, the process monitor, is like a bouncer. If a user's application crashes, PMON jumps in, cleans up their mess, and releases any locks they were holding. And finally, you have CKPT, the checkpoint process. Think of it as the project manager, periodically telling everyone to sync up and updating all the file headers so they're on the same page. Okay, we've met all the components now, the files, the memory, the processes. So let's put it all together. Let's see what actually happens when you run a simple query. So you type your select statement and you hit enter. To you, it's just one click. To Oracle, it's like a starting gun going off. The very first thing that happens is Oracle assigns a dedicated process just to you, for your session. It's called a server process, and it's basically your personal concierge for this entire journey. Now, your personal concierge is going to guide your query through 3 main phases. First, it has to parse it, which is basically, do I understand what you're asking? Then it has to execute it. Okay, let's go get it. And finally, it has to fetch the results. Here's the stuff you asked for. So that first step, parsing, is all about checking the rules. Your server process looks at your SQL and asks a few simple questions. Is the grammar right? Does this table you're asking for actually exist? And maybe most importantly, do you even have permission to see this data? And this is where that shared pool we talked about becomes a total game changer. The first thing your process does is check the shared pool's library to see, hey, has anyone run this exact same query before? If it finds a match, it just reuses the existing execution plan. That's a soft parse, and it is lightning fast. If it can't find one, well, now it has to do a hard parse. It has to build a whole new plan from scratch, which is way more resource intensive. For developers, making sure your SQL can be soft parsed is a huge key to performance. Okay, so our process has a plan. Now it's time to actually execute that plan and fetch the data. The plan tells it exactly which data blocks it needs, but the very first place it's going to look is not the disk. It's going to ask, is this data already in memory? And this brings us right back to our star performer, the database buffer cache. If the process finds the data it needs right there in the cache, that's called a cache hit. It's a logical read. It's fast, it's efficient, it's exactly what we want. But if the data isn't in the cache, that's a cache miss. Now the process has to do a physical read. It has to go all the way out to that slow hard drive, find the block, and copy it into the buffer cache first. The entire architecture is geared towards one goal: maximize logical reads and minimize physical reads. So reading data is one thing, but what about when we want to change things with an update, an insert, or a delete? This is where the architecture's priorities shift from just being fast to being absolutely, positively, unbreakably safe. And this flow right here is Oracle's unbreakable promise to you. It's that write-ahead logging we mentioned. So follow along. Step 1, your process changes a data block in the buffer cache. That block is now considered dirty. Step 2, and this is the most important part, log it first. Before anything else, a little description of that change gets written to the redo log buffer in memory. Step 3, the hyperactive LGWR process immediately grabs that record and writes it to the redo log file on disk. This is a super fast write. The moment that's done, your commit is successful. And finally, step 4. Later on, whenever it's efficient, the lazy DBWN process will get around to writing the actual dirty data block to the data file. It's genius because you get the speed of the fast log write, while the system gets the safety of knowing the changes recorded on disk long before the actual data is updated. So what makes that speedy LGWR process spring into action? Well, it's not just sitting around waiting. It's triggered by a bunch of things. The big one for you, the user, is when you type commit. That's you explicitly saying, hey LGWR, write this to disk right now and make it permanent. But it also has its own internal triggers. It writes every 3 seconds, or if its memory buffer starts to get full. It's a belt and suspenders approach that guarantees your committed work is safe on disk almost instantly.
All right, we've looked at all the individual parts, the files, the memory, the processes. Let's take one final step back and just admire how it all works together like a perfectly choreographed dance.
And really, it is a continuous high-speed cycle. A request comes in, it's planned in the shared pool, the data it needs is brought into the database buffer cache to be worked on. Any changes get immediately scribbled down in the redo log buffer, which LGWR then secures to disk for safety. All the while, in the background, the DBWN is efficiently tidying up, writing the finished work back to the data files. It's this constant interplay that lets Oracle deliver both blistering speed and ironclad integrity.
So this is the ultimate question, right? What happens if someone trips over the power cord? Well, the entire instance, all that memory, all those processes, it's gone in an instant. But the physical files on disk are still there. So when you power the server back up, the SMON process wakes up and immediately goes into recovery mode. It picks up that flight recorder, the redo logs, and carefully compares them to the data files. It then automatically replays any committed transaction from the logs that hadn't made it to the data files yet. And just like that, the database is brought back to a perfectly consistent state. No committed work is ever lost. And that promise, right there, is the entire foundation of the Oracle architecture.